Welcome to Cheap Controls. We make videos on things that we struggled with, hoping to help you so you don't. Consider subscribing and hitting that bell.
In this video, I'm going to go over data collection more than anything because I'm trying to figure out if I can determine RPMs based upon vibration. In order to do that, I'm going to have to capture both vibration data with an accelerometer and RPMs with a Hall effect device. I've spent the last couple of weeks looking into it, and I thought I had it all figured out. I'm using a Nano and a smaller Nextion display, but the Nano is limited in its capabilities, and so I ran into a roadblock there. But I got the basic configuration done, so I'm going to go ahead and make a video, and if nothing else, I'll show you how to use the waveform and how to collect some RPM data. And some of the issues that I came up with I think will help me when I get over to the new device. Now, one of the main things that I found with this is to collect using the Hall effect device and the accelerometer at the same time wasn't great. The Hall effect device reading is fine because I do that every second. So I do a counter and then I figure out or I calculate the RPMs based upon what I collect over a second. But when I go to the vibration, I want to collect the data a lot faster, and I don't want it to be interrupted by that 1 second query on the Hall effect. So what I did is I came up with a status variable, and I call it program_status. And then I use that throughout. And when it's set to 0, that's when nothing's happening. I'm just getting the RPMs of the fan, and it's just operating as normal. But I have a button on the display, and I'll go through the display here in a minute. But I have a button that when I set it, it sets that program status to 1. And then when it's set to 1, I don't do anything but get the variables ready. I have an asynchronous delay for the vibration detection. I set that up, or I zero it. And I also have a timer for the length that I'm going to be taking the data. In this case, it'll be 3 seconds. So I'm going to sample it every 100 milliseconds to begin with for a 3-second period. Once that I have that reset, then I set my program status to 2. And this is where I do the data collection. When I do the data collection, I'm doing it for 3 seconds, and I don't do anything else. I don't write to the display. I don't do anything other than collect the data. And then once I have the data collected, I set my status to 3. And that's when I display all the data. And then once I'm done displaying the data, I set the status back to 0, and I go back to collecting my RPMs and wait for the button to be pressed again. There's not a lot to the Nextion configuration. I have a slider up here that I use to control the speed of the fan. I don't do a lot of speed in this video. I just kind of crank it up and let it go. And then I have this text label here where I have just the label RPMs. And I also have this number field here which shows the RPMs, but I dual function it. So when I'm collecting the accelerometer data, I do show the program status variable. Then I have the waveform itself. I have it set up for 3 channels, just like I had before, but I'm only going to take 2 channels worth of data. I'm just going to record the X and Y. I ran into some limitations on the Nano for storing data, and so I just cut it down to those 2 channels for now. And then I have this button. Both this button to start the reading of the data and the slider have code related to them. For the slider, I send my C:C, and then my command is SPD for speed, and then whatever the value is. And I have this value set from 0 to 255 for the slider. So that way I don't have to change anything. I can just read the data in, get the value, and write it out to my motor pin. And then for this read button, for that one, I just send it as a value. So I send the C:C, and BTN is my command, and then the value is either a 0 or 1 when I press it. So when it gets that 1, it starts the program status to start collecting the data. So as you can see, there's not really a lot to this display, and I have it on a physical display. It's a smaller display, and once again, that's something I want to change. I originally wanted to do it on a larger display, but I thought maybe this would be good enough, but you'll see that it'll be easier to read on a larger display. Now, normally on the Arduino, I type the code in as I go, But in this case, this is a little bit different. I want to go over more of the control and what I did. So if you've seen my videos in the past, I have a standard configuration, and I build off of that. I'm also going to have this code as I'm done with it today. It'll be available up on the Cheap Controls website. You just find it based upon video number 193, and it should be somewhere in there where you can download it. And there will be a link to that blog post in the description of the video. And at the start, I just defined some variables for the display itself. And then I have two asynchronous delays, one for the accelerometer and one for the Hall effect device. And the accelerometer is going to have a few variables with it. And the accel length is the frequency at which I do my data collection. In this case, it's 100 milliseconds. And then my read length, which is 3,000 milliseconds, or 3 second total. And then for the Hall effect, I have the Hall delay and then the Hall length. And I have that set for every second. I won't be adjusting that in this video, but I will be adjusting the frequency that we take the data for the accelerometer. And then I just create some variables to keep track of, or to make it more readable in my code. I have my software serial because I am using a Nano, and so I'm using serial port 2 for the connection between the Nano and the Nextion display. And then for the motor itself, I'm going to use pins 5 and 6. And for the Hall effect sensor, I'm going to use 11. With the Hall effect sensor, I'm going to have to keep track of how many times it's triggered over that second. So I have a counter. And then I also have to know the state, because I don't want to read every state change. I only want to read it when it goes from a low to a high, or a low or a high to a low. It doesn't matter which one you pick, but you only want to read it at once every time it goes around. Now in my case, I have two magnets that I'm reading, so I'm going to read it twice. So when I do my math, instead of for every second it being, for every minute being 60 seconds, I'll just divide it by 30. And then you'll see here I have my program status variable. I'm starting that equal to 0, and that's what's going to tell me where I am, whether I'm collecting Hall effect data or I'm analyzing the accelerometer data. And then I have my wire.h library, and I have some arrays for my X array and Y array, and that's where I'm going to store the data. So as I collect the data, I'm going to push it into this array, and then when I'm done, I'll read it back out of the array. And that's what the X array and Y array are for. My setup is pretty simple. I have two serial ports, one to connect to the Arduino, and then one connect to the Nextion display. And then I set this pin mode 13 to be an output. I use that onboard LED for one of the asynchronous delays, and then that way I can make sure that it's working okay. In this case, I have it tied to the Hall effect since it's going on and off every second. For the motor configuration, I take my two motor pins, set them both to low, and so that way it starts in an off state. For the Hall effect sensor, that's an input. And then in one of my last videos, you can go look at it. This is where I configure the I2C bus for the accelerometer. And then to start the loop, every time through the loop, we're going to count, or we're going to see if the Hall effect has been triggered, and we'll start to count that up. And so that's just going to happen independent of any asynchronous delay. We're just going to collect that every time through the loop. So we'll have to be aware of that, because when we're not wanting to register the RPMs, we'll have to zero that from time to time. And then if I have serial 2 dot available, which means that the Nextion has sent a command, we run this input function. And the input function I have separated on this input tab up here. I read all my commands in the same function, so whatever I'm being sent. And once again, if you're familiar with my tutorials, I've gone over this probably a million times. But I separate out, based upon that C:(C), and then I finish it with a question mark. I separate the command right here and the value right here. And I store those in separate variables. And then I analyze the command down here. And if the command is equal to SPD, I'll take the value and I'll write it out to the motor pin. In this case, I'm using motor 2. If the command is BTN for button, then I'm going to set that program status equal to that value. So when I push the button, I'll set it to a high or a 1, and it'll start the collection of the accelerometer data. And for the Hall effect delay, we're going to run this whenever the program status is equal to 0. And every time we run a delay, we're going to reset this reading start back to milliseconds. We're not going to use it in this one because that's for the accelerometer, but I want to keep it up to date. But then we'll go down here, and if the milliseconds is ready for Hall effect delay to run, all we're going to do is we're going to set it for the next time to run by incrementing it to the delay length. And then we're going to run the Hall effect function. And all of my asynchronous functions are in this delay tab. And then the Hall effect function, we're going to trigger that onboard LED here, and we're going to take that counter and we're going to multiply it times 30. Since we're doing 2 reads for every time the blade goes around, we multiply it by 30, and that'll give us convert our second reading into minutes. We're going to print it on the local serial monitor, and then we're going to also update that number field on the Nextion display, and then we're going to reset it back to 0. And we'll do that every second. If we press that button, it's going to set the program status to 1, and that's going to start a series of events. The first thing it's going to do is it's going to print to that number field where we were printing the RPMs on the Nextion display. It's going to put the program status up there, so it'll set it to 1. And then we're going to reset the reading start data to milliseconds, and we're going to set that accelerometer delay to milliseconds. So in other words, we're going to zero them both out. Then we're going to set the program status to 2. So the next time through the loop, it'll run the next function. And then in the next function, if we're ready to read, which we're going to do every 100 milliseconds, we're going to reset it so it'll read again in 100 milliseconds. And then we're going to run this Excel function. Once again, the Excel function is up here in the delay. Now on this delay tab for the accelerometer function, the first 4 lines tell the I² bus that we're going to collect data from a certain register and how many registers we're going to collect from. And in this case, we're going to do 4. In the last video, we collected 6 registers because each axis has 2 registers. But we're not going to collect the Z one in this one. So I'm just going to collect from 4 writes, and then we're going to shut it off. Or then we're going to disconnect the I²C bus. So we're going to get the X raw data and the Y raw data. And then we're going to take that data and we're going to convert it into floats. So we have to divide it by 8,192. And once again, that's from another video. If you want more on that, you can go back and see that. And that gives us our raw data. But then we have to turn that data into an integer because for the display only can take integers. So we're going to take that and we're going to multiply it times 30 because we also want to display it over a wider range than the data shows. So we don't really care about the accuracy on the Nextion. We just want to get a good representation of it. If we want to use the data later or evaluate it, we can store it differently. But for right now, we're going to multiply it times 30. But we're also going to shift it up because it's zero-based data. So we want to move it above the 0 line. But as I said, we're not shooting this out to the Nextion display yet. We're just pushing it into the array. And we're doing it based upon the X array counter and the Y array counter. Then you notice after we store one value, then we increment the counter. So the next time through, the next 100 milliseconds, it will store it in the next spot. And here's where the reading start and reading length come in. Because not only are we checking this delay, but every time through here, we're going to look for that delay also. And if both of them are true, then we're going to set the program status to 3, and we're going to write out the program status and make it go to 3. If you notice, I forgot to do it on 2, so we'll skip 2. We won't be writing 2, so it'll go from 1 to 3. But it'll still be a good indication on the Nextion display if we've got data. If the program status is equal to 3, we're going to print the number of bytes that's currently in the array. This will give us an indication as to how much data we've stored. We're going to do that just out of the serial monitor. And then we're going to treat each axis separately. So the x-axis, we're going to focus on it first, and then we'll go to the y-axis. And I have some lines commented out here, and we'll get to that later because we're going to expand the data artificially. But for right now, we're just going to print this serial to print the add function, which adds to the waveform, and then the data that we have. And we're going to step through it backwards from the way that we took it. And then we're going to do the same thing for the Y. We're going to step through it. So this will be kind of interesting. You'll see on how the waveform works if you have two waveforms and you send data completely separately. It'll draw the one set of data, and then it'll look like the other one's coming in behind it. And then once all the data is out there, we need to reset that button value or that button setting on the display back to 0 and just change it. It'll look different. It'll look like we tapped it again. We're going to set the Hall effect counter back to 0. And we're going to set the delay. We're going to 0 it out. And we're going to set that program status back to 0 so that it all starts over and we're just looking at RPMs again. I'm going to upload this and show it to you. Now I have this board set up and it has this motor driver over here on it. So I have everything plugged into this. And that's the way I can drive this. You can't just drive the DC motor straight off the Nano. You'll need some sort of a driver board for it. So now I have this all set up here. I'm going to start the fan going, and you can see I'm showing my RPMs here, and I'm hoping they show up down here too. And there you can see I've got the RPMs going down here and on the screen. So now I'm going to move it down and go and just push the button. And you can see that it collects the data over on the side. I'm going to stop this from auto-scrolling. And you can see right here we got the bytes used was 31. So it only captured 31 bytes, or 31 readings, I guess you could say, because it did both the X and the Y, and I'm only showing the X on here. If you do the math and you have 100 milliseconds read time over a 3-second period, that makes sense that you'd only get 100. So the next test we'll do is we're going to make an adjustment. But before I make the adjustment, I want to show you here. I set my arrays at 200 each, so I can store 200 values. And in that case, I took 31 values. So I have plenty of room to store more information in there. What I found is if I went over 200, I'd get a warning from the Nano that I was running out of memory. I'm going to set this at 50. And now when I start it, we should get more values, twice as many technically. And you can see how it comes in across the screen. First one and then the other. So that's kind of interesting. And you can see that we did get more data. I'm going to try and leave the old data up there. Now, in this time I hit it twice, and you can see that the bytes used was 61. So we doubled the amount of space we were using. I'm going to do one more test here. Because what we really want is we want to get as fast as possible. So I've run this at 50 hertz, which is 20 samples or 20 milliseconds. So I'm going to show it to you one more time here. And so we reduced it by more than half this time. Or we've doubled it, more than doubled it this time. 25 would have been doubling it, which would take us from 60 to 120 readings. In this case, we're going to be closer to 150 readings every time we hit the button. And you can see it came across further. Do it one more time. But you can see that the data on the screen is very packed tightly. And you can see that we got 151 readings. And if I were to try and get more readings to show more of a sine wave form, I'm going to run out of space. And that's why I'm going to step up to a different device. I think I'm going to look at using an ESP32 instead, because the Arduino runs at 16 megahertz, whereas the ESP32 runs between 80 and 240 megahertz. So I should be able to sample a lot faster. And it also has more memory, so I should be able to store more memory. So the plan is to get this new device, collect more data, and so then look through it and see if I can figure out the RPMs based upon the vibration. But you can tell that this scale would be really hard to figure that out. There's one more step I want to look at, though, because what I'm going to do is I'm going to try to create the data artificially. So by uncommenting these lines, what I've done is I'm going to take the value, the last value read and the next value that's going to be displayed, and I'm going to figure out 4 steps in between that. So I'm going to take that value, subtract it, so I get the actual value between the 2 steps, divide it by 4, and then I'm going to plot the data points as if they were actual data points. So it should make it look more like a sine wave. And it will also give me 4 times the data on the screen. So you can see I get my diff variable, and I do that by subtracting either the next value from the old value or the old value from the new value, depending upon whether that value is increasing or decreasing. And then I set up a little X counter, a little loop, that'll count through each one of those steps, and it'll take that variable and multiply it by the value of X. So the first time through it'll be 1, 2, 3, and 4. And I'm going to do that for both the X array and the Y array. So I'll upload this and show you. So now when we look at the data points, we should get the same amount of data points, but it should look better on the display itself. And you can see that it's getting a lot more data. It's taking a lot longer to get across the screen. So not only is this easier to read, but the data points, I get a lot more data points. I'm also going to look at adding the ESP32 into the mix and see if I can get even more data faster. So that way I can get more data points and make sure, because this could be missing a whole cycle here, because I'm guessing on the 4 data points in between, but what if there was a spike up and down in between readings? I would be getting mistaken data that way. And then if you're going to do this on using some Lux Blox yourself, what I did was I just glued some magnets on it. I just hot glued the Hall effect device right to the Lux, which is nice. I cut the top off of this, but I really didn't have to. It was nice because the accelerometer just bolts right to the Lux Blox. The pattern just fit the holes perfectly. So all in all, it worked really good using this device. And I use this kit here, this Steam Primer kit. It seems to have all the pieces I'm needing so far to do it. So there's a little plug for my friend and his product. So just a recap of what I did, I was able to collect the data like I wanted. I was able to get the vibration data separate from the Hall effect data, and it worked really well. But I ran into some limitations on the Nano. So I'm going to give this another shot with the ESP32. So I'll come back with another video on that in a couple of weeks and let you know how it's going. I hope you guys find this interesting. I've had a lot of fun playing with it and getting it to work, because I do want this channel to get more into the control functions and things like that.
Well, that's about it for this video. If you like what you saw, consider giving me a thumbs up, and also consider subscribing to the channel. Thanks for watching.